Okay, go ahead, Yaroslav.
Okay, my today's talk is devoted to the area of application of machine learning to molecular dynamics, and particularly I will discuss this paper, like ORP, a framework of modeling mm, neural network potential for molecular dynamics application. And so let me start with some introduction. Basically, data scientists who develop machine learning models in the area of physics, they mostly uh, target the potential energy surface modeling, which is a powerful tool for description of molecular systems, so that this is just a function of the potential energy with respect to atomic configuration as a function of configuration. So here's the example of water molecule, and with all symmetries considered, the configuration space can be described as just by two parameters, which is the length of the bond between the hydrogen and oxygen, and the angle of the bond. And then you can like imagine this surface as for any combination of these parameters in configuration space, there is a value of energy. And so this potential energy surface can allow you to explore the optimal geometry of molecule, for example. If you find the minimum of this potential energy surface, then it will give you some information about like optimal values or characteristic size of the length of the bond, sorry, characteristic like angle. And of course, during the dynamical evolution, those things are somehow fluctuate, but this give you some information about average values to be measured in the experiment and compared. Some quantitative things about the system, about molecule. And then in molecular dynamics, the potential energy can help you to simulate the dynamics, since like in case of conservative forces, this potential is essentially the thing that defines the force that acts on the particular like atom, just by taking the gradient of this potential with respect to position of particular atom, you can obtain the force. And then if you know the previous position of particle, the velocity, and this force, and then you can estimate the future position of particle and perform the molecular dynamics. So let's dive into the details of the particular method, ORP. And basically it's based on the graph network simulator. That was some architecture that was presented also first time in another paper, also for modeling the physical systems, also for molecular dynamics. And here the construction proceeds as follows. So you start with your particles, and they are represented as nodes in the graph, and so you can define the vertices. Each vertex corresponds to each atom, and initially they are just some vector embeddings that are specific to the particular atomic type. So initially, atoms with the same atomic type have essentially the same vector of embedding, and they do not contain those vertices features do not contain any information about the position, and the relative positions of different particles are encoded into the edges on this graph, edges features, and they from one point they consider different Gaussians that they evaluate as a function of the distance between two atoms. And those parameters of Gaussians, they are somehow chosen, and they, as far as I understand, and they do not train them. Those parameters are somehow chosen. They did not explain that in the paper, but so it's not clear how to choose them, but probably in some according to some distributions of them. And so there are those Gaussian features, and also there is a vector feature that is essentially the displacement vector from one particle to another, and normalized by the norm. So it's a unit vector of direction from one particle to another. So it's not really an invariant feature, unfortunately, but that's how they do that.
So the edge is not just a number there; it's a vector.
Yeah, those and vertices also are vectors.
No, I understand the vertices are vectors, but edges are not
Edge is
just
also a vector of quantities.
quantities. Okay.
Some vectors from there's those Gaussians, some features that correspond to the kind of relation between ith and jth atoms.
But they're like three-dimensional vectors or whatever, b-dimensional. Or...
Yeah, multi-dimensional things.
Okay.
And there's also one thing that is also a part of this graph, but it's kind of implicitly, it is this like cell information about the cell. It is used to account the periodic boundary conditions in order to like compute this displacement vector from one particle to another. You just take the nearest image of neighboring particles every time. So this information about the cell is implicitly contributes to this edge construction. All right, and then what they do with this graph is they define their activation dynamics with those features in 3 stages. And the first in these 3 stages are like encoder, process.
Can I ask another question? Sorry, I'm still on those Gaussians. So basically, those Gaussians are kind of sensing, probing certain distances, right?
Yeah.
So the mean is mu L is a scalar, right? And then X is also a scalar. So it's like shells of distances that they're probing, right? So
Yeah.
they kind of they tell you how far things are distributed, but not just by a number, but whether they do belong to the shell or don't belong to the shell, something like that. Okay.
All right, and then the first stage they introduces the encoder part is that we start with those initially with those arbitrary, no, I mean some embedding, and as I understand, they start with just they can do the vertex embedding by like atomic number and something like that, some numbers that describe a particular atomic type, but then they map it into some latent space, some presumably more with more dimensions. They map this vi, the vertex for correspond for each atom. They map it into some other space, and those mapping is trainable, and they do it by using just multi-layer perceptron model with layer normalization. And then they do essentially the same with those edge features, with those Gaussians, They also map it somehow in trainable way to some latent space where they proceed the processor operations, so-called. So they kind of compute the edge residual first, so they just combine, concatenate essentially the edge features in the effective latent space, then the vector of embeddings of two atoms, and that's way they obtain some vector in some space that kind of mm, should somehow describe the effective kind of interaction between ith and jth atom. But then they perform so-called like messages. Those are just for each particle you start to form like the weighted average of those edge residuals according to the psi weights that they respect some cutoff. They introduce some cutoff so that too far away particles do not interact at all. And the function of cutoff is presented here, and I plot here on the right side. And they choose it not like the hard cutoff, but the soft way of cutoff in order to make the predictions of the model like continuous with respect to small perturbations of positions. Since if you have cutoff, then of course you can have some problems on the boundary of your cutoff, and there might be some discontinuities. And here they considered two types of those messages, and those are like received and sent messages. And they constructed this way. And after that, they just use another multi-layer perceptron to like process those messages, and as well as the encoded embedding of each particle in order to obtain some evolution, some future value of this embedding vector, some after those messages being processed. And this is the processor part. It's like one block here, and then they repeat it for some times, like they tried four. Well, I mean 4 steps, but they those blocks are kind of repeated. And yeah,
I'm
I
sorry,
believe here.
Yaroslav,
Yeah,
could you tell us once again what the importance of passing two different messages is?
yeah. I mean, in general, it's because those sets of like which atoms send messages to you and which atoms you message to, those sets are not. They can be different actually sets. Because one particle may be important to the motion of some other particles, but for this particular particle, the set of important particles may be different, and those sets not necessarily are equal.
For instance, if I have a, a carbon ring, one of the hydrogen atoms sticking off of one of those carbons is going to be really dependent on that carbon, and that carbon, but that carbon isn't going to be particularly responsive to the hydrogen. Is that the thought here?
Yeah, in some sense, yeah.
Thank you.
Yeah, interactions are not symmetric in this sense. A can be influencing B, but B would not influence
Yeah, but
A.
the physicists in the world don't like to hear that for every force there isn't always an equal and opposite reaction.
Well, there is force, but it may not be relevant.
Understood.
Yeah, so there's some forces are more relevant than the others, right? Yeah, so I think this is kind of setting up what's more relevant and what's less relevant, because those psi's are normalized, yes. So you want to normalize it.
All right, but then I will continue with the decoder stage, that is about actual mapping from those some latent space of some embedding where some messaging was performed, and then you need to obtain final your prediction for particular physical important quantities like energy, like force, like stress tensor. And this is done by another multi-layer perceptron. And what's interesting is that they just average over all embeddings of all particles in the system and then pass it into this trainable module that gives the energy of the system. Then the force is just a function of particular embedding of processed embedding of particular atom. And I believe here this is a typo, so it should be three-dimensional vector F. And this thing is not invariant actually, so it depends on the choice of coordinate system, and it's kind of not so good thing. But yeah. And also this force is not necessarily is the gradient of this energy actually. So in some sense it's more general approach, so that it can be used for modeling in non-conservative cases, modeling the force. But I believe that particular application that is the result of in the paper that they present, they applied their model to the conservative cases where force is conservative. We'll come to that later. And they also predict this stress tensor that is about some mechanistical properties of the system as a whole. And we know that this tensor is a symmetric thing, symmetric matrix, so that they only predict 6 independent components. And what's interesting is that they use 2 stages of training, and they have some pre-training of the model on some artificial task actually. So they start pre-training their model on denoising task, where they just introduce some abstract system, like some molecular system where you have some atoms located at certain positions, but they do not predict not the force, not the energy, but they just perturb the system with some Gaussian noise, and then train the model to denoise the system, to guess what was the noise. And this is done by producing the sequence of noisy copies of the system with different parameters of the noise, of Gaussian noise, but the system is able to look at those copies, and it should somehow identify the common patterns and denoise essentially the system. So here, this is some strange gradient of some, of some derivative, some logarithm of distribution, but it's actually, if we have this Gaussian noise, then this log of distribution is just this quadratic function. Then taking the derivative, we have this this linear thing, and if we know that xt is just x0 original system, but with some noise added to it, then it's nothing but just this derivative is just the noise itself, with up to the constant. So basically,
so it's like a separate network, like in Stable Diffusion. It tries to learn the noise. Is that?
Yeah. Yes.
Okay.
Yes. And I believe that its network consists on also of these all layers, but the decoder part is different. But the idea is to train encoder and processor, to pre-train them and to use not from scratch to model an energy and force, but to start with something that was pre-trained on this task of predicting the noise. And it's somehow trained some idea of geometry that can be learned. I mean, they have in their results the comparison where they pre-train or not pre-train at all, and the results are different, and pre-training matters. Pre-training helps.
So I think I'm missing something. So what is the data set? Is data set trying to predict how the system will evolve, or the system or predict the added noise so that you can remove it?
First, they predict the noise, but then they just take from those neural networks that predicted initially the noise, they take some part, essentially the encoder and processor. Then they connect with some randomly initialized decoder and train for the force, for energy on the fine-tuning stage.
I see. So first you want to make sure that the noise, you can denoise it whenever you want. And then in addition to that, you're trying to make the prediction for how your system will evolve. Is that the idea?
Kind of, but I mean, the idea is just to not start from scratch. So to have some parts of the model already know something, already be trained on something.
Yeah, but learning the noise and learning how the system evolves seems like two different separate tasks. So and that's
Yes,
why.
they are different, but again, at least experimentally, they proved that there is some connection.
Okay.
So, I mean, to denoise, the model needs to create those internal representation, effective representation of the system. So to have some idea of how to encode, how to which space to choose to map the initial embedding, and then it starts not from scratch, from like completely random latent space, but from some latent space that is better than random, essentially. But those tasks should not really be very connected. I mean, it just turns out to make this pre-training, it's just better to start from completely from scratch. Yeah, so it's actually nothing. This task is nothing to do with physics. It's nothing to do with prediction of forces, energies, but it's. I'm also kind of confused with that. How
No, I think it
really
has to do with the system being stable and not learning the noise. But I'm just not sure I understand the exact architecture here. But it makes sense, right? So you don't want, if you add noise, you don't want that noise to be grow. So you want these directions to kind of be projected out. Are they adding the noise to the latent space or to the input space? To
they
where?
add noise just to the position of atoms, and
Okay,
then
so
those
that's not
positions are
latent.
contribute to these Gaussian features, etc.
But then it may not be a noise. I mean, like you get just different initial state. So that's why I'm confused, right? So I mean,
Yeah, but they considered again the kind of set of copies of the same system, but with different noise, and it should find the similarity between them, find some common pattern, and find what is the noise and what was the original X0.
I think
yeah, but
that this is more in line with like NLP training because this is pre-training. So usually like they do this because you don't have enough data. So you kind of make up a new training task where you have like unlimited data because you can just generate as much as you want, noisy versus not noisy. data, and then it's not labeled because you basically are trying to find what's noise and what's not. And then that's what's called pre-training. And I think this is like supposed to increase generalization to like out of distribution data. But yeah, I think that's kind of like the
I
point.
see.
This may not have any relation at all to your problem. It just
Right.
kind of like, let's build up some more general abstract features for some problem using this architecture, and then we fine tune it on like the actual smaller problem set.
I see. I see. Okay. Good. So yeah,
Yeah,
so that's
thanks.
just then it's just increasing the data set, not.
Yeah, because I think in like transformers they do something similar where they pre-train on like you have your token sequences for
Mhm.
text, and you basically just apply a mask to like 20 or 15% of your tokens in the sequence,
Mhm.
and you try to train your encoder to basically reproduce or guess what those missing 15% of tokens are based on the context of like all the other tokens that it still sees.
Mhm.
And then you can use that encoder, for like predicting next token or some other uh, global property of your sequences.
All right, makes sense. Thanks.
Thanks. Yeah. I actually seen this for the first time, but yeah, that makes sense.
Well, you don't want to add too much of data, otherwise you, as Vladimir said, that it's unlabeled data, right? When you perturb it. So, but yes, adding a little bit, maybe it will help with overfitting, things like that.
Yeah, I think that's what
Okay.
they claim.
Yeah, but then it
I
makes.
personally haven't used this, so I don't know, but
Yeah, sure.
that's what I've been reading about.
Yeah.
Yeah, and then they performed the fine tuning when they took the pre-trained modules of those model for denoising and just add another decoder that actually is trained for actual problem for finding the force, energy, stress tensor, etc.
Mhm.
And here the energy is predicting not just the complete energy, but some linearly transformed thing, but it's essentially like, I mean, we know that energy is defined only up to some constant constant term, and it's unobservable actually. So they kind of use some reference value that they normalize over it, and then in general there is this like understanding that on average kind of energy is extensive parameters that scales with the number of particles in the system. So they try to model like an average energy per one particle. So that the hope is that it can be generalized for larger systems as well, if you even train on smaller system.
But even for larger system, you still have this n square problem, right? Because when you calculate your there's edges.
Yeah, but they have cutoff here. So
Oh, I see.
yeah,
Sharp cutoff.
not so sharp, but yeah, I mean, at some point it's sharp. Yeah.
So they're not doing something like logarithmically less, further away,
No, no,
uh,
no, 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 no.
logarithmic less. So you can like presumably create a hierarchy which will be better than a sharp cutoff.
Yeah,
Okay.
exactly. All right. And then that's interesting that their loss is not like mean squared error loss, but it's linear mean absolute error loss. So the one of possible explanation is that there are some rare outlier cases when something goes wrong, some energy locally may grow, or the force can be too large for some at some points, and maybe those outliers contributes in learning in a bad way, so they choose this mean absolute error loss.
Yeah, but energy is usually like quadratic function of velocity and position. So secretly it is L2 mean squared.
Yeah, probably. Yeah.
So you already have squares in the energy.
But I mean here for force, for example, they use this mean absolute error.
Oh, I see.
If your force is like the gradient, then it's linear thing.
Right. Well, it's a gradient of, again, energy, and so energy has all those yeah, but you're right, it would be linear. Yeah. Yeah, I don't know if this is, and why they do that. Why don't they do L2 or like mean squared?
I mean, I tried to explain it by there are some outliers, and then if your loss is quadratic, then those outliers have more participation than needed, probably.
I see.
Kind of this explanation, but I'm not completely sure. And I believe that's at least experimentally I believe they
Okay.
observed that just this loss works better. Okay. And then the total loss is of course some linear combination of those, and for stress tensor is similar mean absolute error loss, and they for some reason use the very same coefficients between like force and stress, but for energy they used another scalar factor weight to balance, as they say, contribution.
But if it's linear, then it's really discontinuous. This loss is discontinuous around small. And then what will happen once it will just keep jumping left and right on this. Like you can imagine the wedge, right? It will never get to the minima because of that linearity. So presumably there is some kind of uncertainty and fluctuations at small losses.
Yeah.
Okay.
Is that mitigated by the other loss terms being smooth at that point?
Well, the other losses will go to zero, right? But then there'll be one term which will be fluctuating, and that's that. I mean, if you are not so precise, maybe it doesn't matter. But yeah, I don't think you can get rid of that fluctuations. It will be just like some terms of the loss function will be very small, and there will be this L sub f that will remain large. But maybe that's not the precision they're looking for, and so it's fine then.
Okay, then there is this issue with that force is not constructed as a gradient, and if we want to make it conservative to preserve some conservation of energy properties, then the idea is to artificially, on top of the model, make some changes in predictions of force. For example, perform this removal of net force to make the total force, sum of all forces, equals to zero, and this is in great correspondence with the third Newton's law. For the conservative forces, it's correct.
So that answers Dan's question. Yes. Sum of all forces is zero. Yes.
Then there is also a torque, like a momentum of force, that is also needed to be removed in order to system to not rotate. And for this problem for non-periodic boundary conditions is correct, but for periodic boundary condition is kind of ill-defined, well, because it's hard to find the center of mass of such systems that is infinite, and maybe some. So they do not do that for case of periodic boundary conditions.
So I have a general question. All this sounds very classical, right? Sum of forces equal to 0 and torque is equal, it remains constant, but they are simulating a quantum system. So why do they think that this, I mean, I understand that the total energy would have to be constant, but why do you want to impose this constraint if it is a quantum system? I mean, they're not talking about like a bunch of point particles interacting by some conservative forces. They're talking about quantum system that is being modeled through the neural network. Okay, are they talking about anywhere about the quantum versus classical here or no?
Not really, not really. I
Okay.
didn't find in their paper such
Okay.
things. Um, so yeah, they just assume that for their systems, they have an effective potential that is that gives some energy to be conserved and
Yeah, but even if there is some potential, there's still wave function for each particle.
Mhm.
Well, maybe for the nuclei, they can be modeled as point particles, but they're still electrons. And are they actually?
Isn't
They're not doing anything about electrons, are they?
Yeah, they mostly in most approaches, as I have seen, they all did not consider electrons at all.
Okay.
they're incorporating the electron behavior through the density functional theory, aren't they?
That's the idea, right? But then why do we want to impose those constraints? That's where I'm getting lost. So
That's more or less your training data. That's the only point you're injecting reality into this.
yeah, but why would this constraint is a reality if the particles are actually interacting through the electrons, which are intrinsically quantum? I mean, I just don't understand why this constraint is needed. I mean, maybe it will be satisfied an average, but I don't know if it has to be satisfied actually at each
Yeah,
moment.
on average, they want the sum to be equal to 0.
On average, I mean time average, but here you are saying that it has to be satisfied exactly, right, all the time.
Mm-hmm.
I mean, I see no problem with those forces, fluctuating around this quantity to fluctuate around 0, given that the interactions are
I
done.
see, I see. Yeah, exactly.
Yeah.
Yeah, maybe. But
It
that's
seems
some.
to be too
That's
restrictive.
one of possible simplifications. Maybe you will have like some subpart of the system has non-zero, and some other part, but as a whole, I mean.
Well, but then again, you can weaken the constraints, have this satisfied locally with some fluctuations. Then maybe this is again doesn't constrain much, and you can make it better. Have this quantity be on average 0 locally, not globally, and then we still have some width fluctuation, some variance. Well, okay.
Well,
I don't
maybe
know.
the idea is that you can experimentally observe that yes, those things are fluctuating, but if you remove those things at all in your modeling and your simulation, then still the results of simulation would give you good results in terms of other macroscopically observable properties.
Yeah, but usually the
So
fluctuations are most important.
the dynamics.
I understand, but then you're taking really classical limit. Uh, yes, this will happen in classical limit, but I thought the idea is to have some kind of semi-classical calculations where some quantum effects are still preserved. Uh, and here you would just kill it totally.
I'm not sure that totally. I mean, some properties of quantumness may be captured.
No, you're right. I didn't say totally, but yeah, of course, some of them will be preserved in this whatever neural network that you was trained.
Yeah, these things, maybe they are like, maybe they will kind of prevent you from taking a reasonable results in terms of numerical errors that will grow. Maybe those fluctuations will somehow multiply it. I'm not sure.
Yeah, but for a large enough system, I think this will still be okay, the constraint.
Yeah. All right.
Okay.
So here are some details how they come to those things. So they want also to perform some perturbation of the predicted forces by some delta F. They want also it to be a zero net, zero average value. This is first constraint. Then they want the torque to cancel, so that the torque of this addition should be negative torque of original forces, and they come to the minimization problem, optimization problem with those two constraints, and they want to minimize this L2 norm of this perturbation, and one can solve it and obtain the result for this perturbation, how it should be constructed based on total torque of original forces and the positions of all particles with respect to center of mass. And yeah. And those torque removal helps as they show in the results, and I will go at some point there soon. Yeah, so I'm mostly focused here on the molecular dynamics, and then essentially as they modeled the potential energy surface as well, as they also applied the method to some geometry optimization problem where you just want to get an idea of the geometry of particular molecule, what is the minimum of the loss surface. And another application is, as I said before, this molecular dynamics. So to use the model to predict forces and then to simulate the dynamics of the system. And there are some metrics they concern about the stability, is how long you can perform the simulation without the system breaks apart, essentially. And this can be defined as large growth of interatomic distances, for example, or growth of velocities of energy, kinetic energy, or something. And so they at some problems they observe nice results with respect to other methods. Then another metric here is this Wasserstein metric that is about two distributions. One is the interatomic distance of during molecular dynamics of machine learning approach, and the ab initio classical quantum computations based on density functional theory. And so you can evaluate what is the distribution of interatomic distances through the dynamics and of two approaches, kind of ground truth, ab initio trajectory, and machine learning driven approach. And Wasserstein metric is essentially that just this integral where you take two distributions. This f is cumulative kind of distribution function, is integral of p of x from minus infinity to x, and you just integrate the difference, the absolute difference of those things to obtain this metric. And if the distributions are the same, this metric will be zero, and if those distributions are different, then it will be larger, some other value. All right, they also compared the mean absolute error for the force. Well, not even normalized, but some quantity, not so interesting. All right, but so here's some results. This is the plots that can help to understand the importance of pre-training. So those are the results of different runs from left to right. The left bar is about training without pre-training on denoising task, and then you can gradually take layers from a pre-trained model, and you can gradually take it from pre-trained model to your actually model that you want to train, and you observe that your loss of the energy goes down if you introduce more and more pre-trained layers, and your error for the forces also goes down. And so in this way they show that pre-training helps with respect to not pre-training and start from scratch training, fine-tuning the model. It worked on two different data sets that they considered. And here is the results of molecular dynamics. Here the data set is this MD17. It's actually not so hard data set. It's only about modeling the dynamics of isolated molecule, just one molecule. It's completely isolated and floating in vacuum, and then you just need to predict the dynamics of this molecule. And for different molecules, this data set consists of different molecules under different conditions, under different temperatures, and just one molecule.
But then there is no edges, there are no graph there.
Yeah, here there is no
Okay.
periodic boundaries.
That's not what their aim was.
Graph is there, but there's no periodic.
A graph with one node.
No. You mean, I mean, each node on the graph correspond to one atom.
Oh, well, okay, small graph. So what kind of molecules are they talking about here?
Like this aspirin, ethanol, like.
Oh, okay, I see. Okay, I take it back.
Some
Yeah.
organic, some
Mhm.
organic molecules. And under different conditions, and these are some average values of those quantities, like stability. So the task is only about prediction for 300 picoseconds, as far as I remember, and the orb performs well during all this limit of 300 picoseconds. And this is this age metric, this Wasserstein like distribution metric, similarity of distributions, and they also show some like good results with respect to other approaches, like kind of comparable to the state of the art, I believe. And then this is also an error of the force here, which is not so representative since it's in some units of that they should be like normalized with respect to average forces probably. All right. And then there is also an interesting approach that they also consider it is the zero-shot learning. It's then that they do not train for those aspirin, ethanol, they just train on some other system. I'm not so sure. They trained like their models for some other systems with periodic actually conditions, and then they apply those trained models to another molecules that are completely outside of training dataset, and they achieve some also nice results here, and well, I mean, with comparison to the other methods. And there is also one interesting comparison that they considered, like the results without removing of this net torque, and those results are much worse, like twice as worse. So this net torque removing is really helping to achieve better quality of molecular dynamics. And there are also presented some results about modeling like this MOF5 crystal structure that is kind of metal organic molecule that has some properties, some extreme values of, I believe, the ratio of surface over the volume of the structure, and they performed the molecular dynamics of the system with gradually increasing the temperature, like to explore at which point the system will fall apart. And they observed that at some point with some temperature, they observed that falling apart the structure. Maybe that's, I believe that's, as far as I understand, that is what observed experimentally, that at some temperature the crystal structure breaks. So they, in some correspondence with experimental results, but I'm not sure that they got exactly the right temperature, critical temperature, but
But hold on, the experimental result is above and the numerical is below, right? That's what you're thinking?
Not really. Those all results is about this numerical simulation.
Numerical, but they're different clearly. In one case, there is this.
There's different things that plotted here. There's one is temperature, and another is like this, some deviation, some geometrical deviation of average distances between particles or something.
Oh,
like
okay.
that. So that from like initial structures, the system has some initial geometry, and then you observe how with more and more temperatures the crystal structure breaks, and a reasonable range of temperatures the structure remains more or less stable, and then the crystal falls apart. Okay, that's I think all from my side.
Yeah, we are running out of time, so
yeah.
Thank you, Yaroslav.
Thank you.
Questions, comments? Dan, go ahead.
No.
Oh, it was not the question.
Thank you so much for sharing this with us.
Thanks, Dan. All right. Other questions? Well, I guess we've asked all the questions. Thank you, Yaroslav, and I'll see everyone next week. Thanks.